Okay, in section 4, we're going to start looking at some more properties of graphs and functions, and we're going to talk about the symmetry of some functions and even odd functions. So you've probably seen symmetry in geometry and some other places, but symmetry is going to be where you have basically the same thing on top of each other. So you can think of symmetry as kind of like a fold line, where you fold it over a line. We'll also talk about where you can fold a graph over a point. So you can have symmetry with a point. So there are lots and lots of symmetries. You can be symmetric to a bunch of lines, a bunch of points, but there are really only 3 that we really care about in math. So we care about when you have symmetry with the x-axis, the y-axis, and when you have symmetry with the origin. So you can have symmetry with the x-axis is if you have a set of points where they flip over the x-axis and the graph would land on itself. So for example, this point here would land exactly on this point if I flipped it over the x-axis, if I kind of flipped it down there. This point here would kind of flip down to here, this point here would flip down to here. So all the points on the graph, if you flip the graph over the axis, would land on itself. And there could be more graph to it. Maybe this goes this way and this goes this way. That would make it symmetric to the x-axis. Now, obviously, the one thing about symmetry with the x-axis, that would always be non-functions. Because if it's a symmetric with the x-axis, it obviously would fail the vertical line test. Same thing with y-axis symmetry. So here's our y-axis. So if I think about some points here, if I flip them over the axis, they would have to land somewhere over on the other side. And then finally, origin. Now, origin or a point is kind of weird because you're flipping it over this point. Now, being symmetric to the origin, you can also think as a 180-degree rotation. So if you rotate it 180 degrees, does it land on itself? Or if you think of this point here, flipping it over the origin would be here. Taking this point and flipping it over the origin would be here. So you're kind of flipping it over this point, or you're trying to flip it over this point. Okay? A little more difficult to see, so a lot of times people will say the 180-degree rotation is a little easier thing. So if I rotate it, it would end up on the same spot. So these are the 3 main types of symmetry we're going to do, and obviously these can be really, really easy if you have a graph. But we also want to be able to verify these algebraically, tell if a relation is symmetric to one of these without graphing it. So here are 3 types of graphs. We want to talk about the symmetry of each of these. So the first one obviously does show symmetry, and I would say it's symmetric kind of to this line here. So I would just simply say this has y-axis symmetry. The parabola on the right, which is kind of looks like this. So if you think of these points all seem like they are getting flipped over the x-axis. This is x-axis symmetry. This last one is kind of this parabola, this kind of, not parabola, cubic kind of looking curve. So it's definitely not x-axis, because x-axis, if I flipped everything over the x-axis, it would look like this, and that's not the same graph. If it was y-axis, it would also look like this, ironically. So it's not that, but it is origin, because if I rotate everything 180 degrees, all the points would line up. And again, we'll have a more definitive test for that here in just a second. Now this one also has symmetry, right? So if you look at the symmetry here, though, the symmetry almost appears to be straight down the middle, right? So this has symmetry to, looks like the line x equal 2, but that's not one of our symmetries we're looking at. So we're really looking at y-axis, x-axis, and origin. But you can see that there is symmetry here. If you remember from Algebra 2, this line is literally called the axis of symmetry. So axis of symmetry, the line that kind of splits your parabola into 2 parts. Now you can also do this with a point, because really all these graphs are just a bunch of points. You can kind of see patterns on how these points move, and that'll help us kind of determine our tests for symmetry with the x-axis, y-axis, and origin. So let's say we have an ordered pair, -2, 3. So negative 2, 3 is going to be in this quadrant. Negative 2 is in quadrant 2. So let's say I want to find a point symmetric to this, to the x-axis, y-axis, and origin. So if I want to find a point symmetric to the x-axis, it's going to flip over the axis, so it's going to go down here to quadrant 3. So it's going to have to go down here. But what's more interesting is if you look at this x-axis symmetry point and see how it relates to the first point. So you can see that it has the same x, still negative 2, but the y has to be the opposite. So for x-axis symmetry, it appears the x stays the same, but the y changes signs. Same thing if I do y-axis symmetry. If I do y-axis symmetry, I'm obviously going to flip it over here. So this is y-axis symmetry. So this appears to be the point 2, 3. So interestingly enough, you can see in this case, when I flip over the y-axis, the y value stays the same, but the x value changes. The x value changes from negative 2 to positive 2. And then finally, if I'm flipping over the origin, you can kind of guess it's going to be down here. This would be our origin point. And if you look at this origin point, it's going to be 2, negative 3. So based on this original point, negative 2, 3, both the x and the y change. So this is how this kind of works with these different kinds of symmetries. The numbers are the same, it's just the signs change depending on which axis you are symmetric to. So this is kind of the foundation of how we'll test equations to see if they have symmetry before we obviously graph them. So if I want to test for symmetry, it's just what we just said. If I'm symmetric with the x-axis, then if I replace y with negative y, it should simplify to the original equation. Okay? So remember, if you're going over the x-axis, if it's symmetric here, then you have the same x, but y and negative y would give you the same value. So replacing y with negative y should give you the same equation. For y-axis symmetry, same idea like we talked about earlier. If I replace x with negative x in this, because x and negative x should both give the same y value. So replace x with negative x, it should give you the original equation. Same thing with the origin. If I think about the origin, so here's something symmetric to the origin. So if I replace x with negative x and y with negative y, because remember, that's what we said was symmetric on the previous slide, then it's going to be symmetric to the origin. So this is very key. So replacing y with negative y for x-axis symmetry, x with negative x for y-axis symmetry, and both for the origin test. Okay? So we're going to try this with a couple different equations, and obviously I know we could graph it. We could graph it and see this very easily, but we want to actually show this algebraically. Then we could graph it, check it, and see what it looks like. So I want to test the following equations with symmetry about either axis or the origin. So I'm going to check for all of them. So I'm going to check for x-axis symmetry, y-axis symmetry, and symmetry with the origin. Okay? I'm going to check for all three. So this is y equals the absolute value of x. So recall what we said above. If you're checking for y-axis symmetry, we will put negative y in for y. We'll put negative y in for y, and hopefully it will simplify back to the original. So if I do so, I'm going to replace y with negative y and leave x the same. Now the question is there any way to get this negative to go away, to turn it back to the original? I'd love to turn it to look like this again. Now, the only thing I can really do is I can multiply both sides by negative 1. I can move. But moving the negative over there still does not give me the original. So this does not go back to the original, so this is not symmetric to the x-axis. And that's okay. That's okay. So, not symmetric to the x-axis. Now, let's try the y-axis. Now, for y-axis, we're going to put negative x in for x. So if I do that, I get y equals the absolute value of negative x. So now we have to think about a little bit about what is absolute value. Absolute value is distance from 0. It always makes things positive. So let's think about this. What if I wrote this as absolute value of negative 1 times x? Because I'm just separating the negative 1 and the x. They're both under the absolute value, so I can separate them. But the absolute value of negative 1 is just 1. So this gives me absolute value of x. So when I put in negative x, it still simplifies back to my original equation. So this is symmetric to the y-axis. And if you know what this graph looks like, that shouldn't be surprising. We'll talk about that here in a second. Now we can check the last one. We can check origin. So if you remember origin, we're going to put negative x in for x and negative y in for y to see what it simplifies to. So that's going to give me negative y equals absolute value of negative x. Now, of course, the right side I already just talked about. That will simplify to absolute value of x. But now I'm kind of stuck. I can't get rid of that negative sign. So this is not symmetric to the origin, only to the x-axis, or y-axis, pardon me. So those tests tell me that only the y-axis shows symmetry with this graph. Now, if you think about what this graph looks like, you should know this. This is from section 1. An absolute value graph simply looks like this. It's like a V. And a V obviously is only showing symmetry to the y-axis. Okay? Okay. Let's look at the other one. Now this next one is a reciprocal function, which obviously we know what a reciprocal function is. It's one we dealt with before. So let's check the reciprocal function for x-axis, y-axis, and origin symmetry. Now again, I don't want to go ahead and jump forward and graph it, even though you probably kind of know what this looks like too. Let's go ahead and go through the test. When we do some of these in class, we'll definitely look at some more difficult examples, but I figured these were kind of nice ones because we knew what the graph looked like pretty easily. So again, x-axis, we're going to place negative y in for y and see if it's the same. So if I do that, it is going to be negative y equals 1 over x. Well, there's not really a good way to get rid of this negative. I could, of course, multiply both sides by negative 1 again, but that's not going to get me anywhere, so this is not symmetric to the x-axis. If it doesn't turn out the same, then it's not symmetric. Y-axis, we're going to put negative x in for x, same idea. So if I do that, y equals 1 over negative x. But again, there's no way to get rid of that negative. I mean, I could put it up in the top like this, but that's still not the same as the original. So we are kind of stuck. So this one is not symmetric to the y-axis. Finally, we have the origin. Now origin, same idea. So we'll have negative, so again, negative x in for x and negative y in for y. So negative y equals negative x. Well, the nice thing now, if I multiply both sides by negative 1, I get negative 1 over negative x, which is 1 over x. So that one's good. So this is symmetric to the origin. It'll show that rotation. So 1 out of 3. Now both of these have been 1 out of 3. It can be all 3. It can be 9. It can never be 2 of them. It can be 0, 1, or 3. Now the graph of this looks something like this. So obviously that shows the rotation, the symmetry with the origin. Negative now. Okay, the last topic we're going to look at is what are called even and odd functions. So we all know about even and odd numbers. So there are some functions that can be considered even, and there are some functions that can be considered odd. There are also some functions that can be considered neither. So we consider a function even is if I plug in negative x. So if I take f of negative x. So remember, That means I'm going to plug in negative x where I see x. I'm going to go ahead and write that down. Negative x in for x. If I plug in negative x for x and I get the original function, then we call it even. A function is called odd if we plug in negative x, f of negative x, so I'm replacing x with negative x, if I get the opposite function, right? So this is the same, this is the opposite. Now an opposite function means all the signs are opposite, right? So all the positives become negative and all the negatives become positive. That is what the opposite is, okay? So if you want to know if a function is even or odd, you can simply just plug in negative x and see what you get. Do you get the same? Do you get the opposite? Or do you get something else? Okay. So I have 3 examples here. I'm pretty sure one is even, one is odd, and one is not. So it's going to be our task to try to figure out which is which. So if I'm going to do that, so I'm going to first look at f of x equal x squared plus 2. So I'm just going to say, okay, if I'm doing this, then what is f of negative x? So I'm going to replace negative x in for x and see what happens. Now negative x squared means I'm taking negative x times negative x, so 2 negatives are a positive. So it's going to become positive x squared plus 4. Now do you notice that is the exact same as we started, right? So this is equal to f of x. So because when I plugged in negative x, it did not change the equation, it's still the same, then I would say this is an even function. It's an even function, okay? All right, let's look at the next one. So if I look at this one, f of x equals x cubed plus x plus 2. Let's go ahead and take a peek at this one. So if I plug in x, negative x for x, I get negative x cubed plus negative x plus 2. So let's simplify and see what happens. So I get negative x cubed, because if I multiply 3 negative x's, I obviously get x cubed, but 3 negative 1's multiplied together will give you negative, minus x, and then plus 2. So let's talk about this. Now it's obviously not the same as this original, right? It's definitely different than that. So it's not the original. It's also not the opposite. For it to be the opposite, all the signs would need to be opposite. So this positive turned to negative, this positive turned to negative, but the 2 is still positive, right? So this does not equal the opposite function or the original. So we just simply say this is neither even or odd. So this is a little different than numbers. If you talk about numbers, at least integers, almost everyone is even or odd, right? But then if you talk about fractions, is 4/3 even or odd? We don't really know. So same thing with functions. Some are even, some are odd, but then you get these some that are neither. So I'm going to guess that this one is odd just so we have one of each, but we can certainly go ahead and check that out. So if I replace x with negative x, I get 2 times negative x to the third minus 6 times negative x. So 3 negatives is a negative, so this becomes negative 2x cubed, because negative x is negative x cubed, times 2 is just negative 2x cubed, plus 6x. Now if you look at our original function, this was positive, now it's negative. It is positive. So this is equal to the opposite function, so this is an odd function. So if it equals the original, it is even. If it equals the opposite, all signs the opposite, then it's odd. If it equals something else, it's neither. Okay. Last thing is, there is a cool way to check this, and that's what's called the even-odd symmetry theorem. Now, this is going to use a graph, and again, we were trying to do this without a graph, which we did, but you can check it with a graph. So a function is even, so even functions always have symmetry with the y-axis. So if I look at the graph of this, it's not a very complicated graph, it looks like this. And that does have symmetry with the y-axis. Again, that's why it's an even function. Now this function, x cubed plus x plus 2, I don't 100% know what this looks like, but it looks something like this, right? So it is definitely not symmetric to the origin, and odd functions have symmetry to the origin, and definitely not with the y-axis. That's why it's neither. This one is 2x cubed minus 6x, so it's going to look something like this, if I'm not mistaken. So this one, if you rotate it around the origin, it does have symmetry with the origin. And remember, if it's odd, it has symmetry with the origin. And if it's even, it has symmetry with the y-axis. So that's kind of a cool theorem. So if you do the algebra for even and odd, you can always check it by looking at its graph. So just a little bit about some of these graph theories. We will, of course, work on some more of these in class on section 1.4.